Hi all, welcome back to software engineering course. Let's get started. Today we will begin with detailed design. So in the previous classes we had discussed two different approaches for system designing. One was based on the functional abstraction and another one was based on the objects, that is object oriented design. So in system design we concentrate on the modules in a system and how they interact with each other. So once the modules are identified and specified during the high level design, the internal logic that will implement the given specification can be designed, and it is the focus of this section, that is the detailed design. So here in the detailed design, the activity is often not performed formally, and basically this is archived as it is almost impossible to keep the detailed design document consistent with the code. So due to this, developing the detailed design is useful for more complex and important modules and is often done it is informally by the programmer as part of the personal process of developing the code. So here we have two types. One is the logic or the algorithm design. The other one is state modeling of classes. Okay. So first we'll look into logic or algorithm design. So the basic goal in detailed design is to specify the logic for the different modules that have been specified during the system design. Specifying the logic will require developing an algorithm that will implement the given specifications. So here we consider some principles for designing algorithms or the logic that will implement the given specifications. So the term algorithm, what is an algorithm, right? The algorithm is a finite sequence of well-defined steps or operations, each of which requires a finite amount of memory and time to complete. In this definition, we assume that the termination is an essential property of the procedures. From now on, we will use procedures, algorithms, and logic interchangeably. Okay, whenever I say procedure, algorithm, and logic, so it means the same thing, right? Next, we will study about the steps in developing of the algorithm. The first one is statement of the problem. Okay, now the problem for which you are building the algorithm, it should be precisely and clearly stated and properly understood by the person responsible for designing of the algorithm. For detailed design, the problem statement it comes from the system design. That is, the problem statement is already available when the detailed design of the module commences. The next step is the development of mathematical model for the problem. So in modeling, what happens is one has to select the mathematical structures that are best suited for the problem. It can help to look at other similar problems that have been solved. So in most cases, the models are constructed by taking models of similar problems and modifying the model to suit our current problem. The next step is designing of the algorithm. So in this step, the data structure and the program structures are decided. So once the algorithm is designed, its correctness should be verified. So, for developing or designing of the algorithms, no clear procedure can be given. The most common method for designing the algorithms or the logic of a module is to use the stepwise refinement technique. Now, this stepwise refinement technique, what it does is it breaks the logic design problem into a series of steps so that the development can be done gradually. The process starts by converting the specifications of the module into an abstract description of an algorithm containing few abstract statements. In each step, one or several statements in the algorithm developed so far are decomposed into more detailed instructions. The successive refinement it terminates when all the instructions are sufficiently precise that they can easily be converted into program language statements. We should understand that during refinement, both the data and the instructions have to be refined. A guideline for refinement is that in each step, the amount of decomposition should be such that it can be easily handled and that represents one or two design decisions. Okay. So in detailed design, it is not specified using any formal programming languages, but using languages that have a formal programming language like the outer structures, your loops, conditions. So, but a freer format for internal description. This allows the designer to focus on the logic and not its representation in the programming language. Okay. So we have you guys already know how to develop an algorithm and how to uh, use algorithm and convert it into a flowchart. So it should be rather easy for you to write this algorithm. The next one is state modeling of classes. So for the object oriented design, the approach just we discussed for obtaining the detailed design can be used for designing the logic of methods. But a class is not a functional abstraction and cannot be viewed as a collection of functions or methods. The technique for getting a more detailed understanding of a class as a whole without talking about the logic of different methods has to be different from the refinement based approach. So, a object of a class has some state and many operations on it. To better understand a class, the relationship between the state and various operations and the effort of interaction of various operations have to be understood. So once you have understood the overall class, the algorithm for its various methods can be developed. So we have a method to understand the behavior of the class is to view it as a finite state automata, FSA. Okay. Now this finite state automata it consists of the states and transition between the states which takes place when some events occur. When modeling an object, the state is the value of its attributes and an event is the performing of an operation on that object. So you have an example over here. This is a state diagram. Okay. So in this state diagram, the events and the states are shown. That is states are shown as these circles and having the name, and events are the arrows. Okay, like this. Or, or like this one. So I'll explain this example later. Fine. Now in the state diagram for an object, it will generally have an initial state from which all other states in the FSA are reachable. So your state diagrams it try to attempt to represent only the logical states of the object. So a state diagram for an object it does not represent all the actual states of the object as there are many states possible. So it will only represent the logical state. The logical state of an object is a combination of all those states from which the behavior of the object is similar for all possible events. Now I'll explain you this example. Now this is a state diagram for your stack operation. Um, you might know what is a stack. You have studied that in data structures, right? So this is the stack operation. So first thing what we'll assume is like the initial stage is the stack is empty. Okay, the empty stack is represented like this. So on an empty stack, if you try to pop, what will happen? If you try to remove or if you want to remove a data from that empty stack, what will happen? You will get a pop error message, right? Whenever you try to pop from this empty stack, you'll get a error message. Now say suppose on the empty stack you push something, right? You push something, what will happen in that case? So you will enter a state that is a not full and not empty stack, right? So you had studied stack like this one, right? If this is a stack, you have if this is a stack, whenever this is empty, so if you try to pop or remove something from this, you'll get an error. So on this empty stack, you push something, you enter some data, suppose 8. So what will happen in this case? Now your stack is neither empty not full. Understood? And now from this state, okay, from not empty not full state, if you again remove this data, you pop this data here. If you pop this data, what will happen? You will again reach the empty stack. Fine. Now we will consider this state as itself. Say suppose we have some values over here. Okay. Whatever. Okay. Suppose we are in this state, not full and not empty state. Now on this stack, if you try to push something, okay, let me just remove this one. Let me just remove this value. Fine. So on this not empty not full stack, if you push something, you can add it. If you remove something, again it would be under not empty not full stack itself, right? You have push and pop operation here. These are the events on this non full and non empty stack. Now, if say suppose there is only one room available, okay, and you try to push something here, or say suppose, yeah, if you try to push some data over here, so what will happen in this case? So 5 you have pushed. So now your stack is full, right? From non-empty non-full, if there is only one room for the data and if you enter the data, what will happen? You'll enter the full stack state. Now on this full stack, if you again try to push something, what will happen? You get a push error message, right? If you try to push something on a full stack, you get a push error message. Now if you pop something, what will happen? Say if you have removed this one, what will happen? Then you'll enter again non-empty, non-full stack or the state. Okay. Now this is the basic diagram, or this is the basic example for your state diagrams. So now let's see about verification. Now this is the last topic in your chapter. So we have already studied about designing, right? Function oriented, object oriented, then about the detailed design. The last topic is verification. Now the verification shows the detailed design meets the specification laid down in the system design. The output of a design activity should be verified before proceeding with the activities of the next phase. If the design is expressed in some formal notation for which the analysis tools are available, then through those tools it can be checked for consistency. Okay. If the design is not specified in a formal or executable language, it cannot be processed through tools, and other means of verification have to be used for this one. So we have three verification methods. Those are design walkthroughs, critical design review, and consistency checkers. Try to give if there are any errors. So these are the compilers that take input as your design specified in a design language. It has to be, the design of the system has to be in some formal language. Then only you can use these consistency checkers. So these checkers, they ensure that the module invoked or module used or given by a module actually exists in the design, and that has the interface used by the caller is consistent with the interface definition of the called module. This is nothing but your compilers, this consistency checker, it will check whether from a module you have, say suppose you are calling basic function call. So if the function call is proper or not, whenever the function is called, whether its definition is proper or not, is there an interface or not, these things are checked. So apart from that, it will also check the global data items, whether they are indeed defined as global or not. They can also use to compute the complexity of the modules and other matrices, because these matrices are based on the alternate and loop constructs which have a formal syntax in PDL, that is program design language. Now the trade-off here is that the more formal is the design language, more checking can be done during design. But the cost is that the design language becomes less flexible and tends towards a programming language. It is always better to have a proper structure rather than having the design in the programming language. Okay. Next, we will have a quiz. So the question is, what are the three design verification methods? So you have got a minute of time to respond. Okay, time up. Now this completes your fourth chapter. Okay, from the next class onwards, we'll start with the fifth chapter. Thank you.